So thank you very much for joining this webinar from Verist Engineering. My name is Sean Teller. I'm a partner here at Verist Engineering, and we're going to get into the presentation here right away. So a little bit about me, if you don't know, I have my PhD in solid mechanics from Brown University, and there I worked on a tissue engineering project where we were looking at the mechanical response of very soft tissues, and the group was trying to develop new tissues to replace the vocal folds. And my role in that was kind of understanding the mechanical behavior, testing synthetic replacements as well as natural tissues, and understanding how the mechanical behavior of those materials impacted their functions. I spent some time with working at Intel in Arizona in high volume manufacturing, and I've been here at Verist, and I'm now a partner. And I spend my time split fairly evenly between pure testing projects or doing finite element simulation, typically of polymers, or in between there, which is what we call material model calibration. So it's taking that test data, finding out the parameters you need to simulate your material, and then a lot of times doing that simulation for our clients. I do like to teach these courses, both these free webinars, but I do paid courses as well, which you'll see in a few slides. And I also give a paid polymer modeling class through NAFEMS, which is an international organization on finite element simulation. A little bit about Verist. So you can see some images there over on the right talking about the expertise that we have in-house. But we partner with our clients to help them understand their needs for their particular product or process or R&D effort, and use the tools within our toolbox to help them solve that. So we have a collection of, subject matter experts with people with PhDs and experience beyond that in their fields. And we use those skills, and that could either be with simulation, testing, or failure analysis to help them understand how their product is going to perform and improve that performance. Or if they have a failure of their product, help them understand what's happening there. We like to say that we do academic expertise, but on an industrial timescale. Our clients want answers, in a week or a few weeks, and we do our best to do that. So we work in a few different areas. We do a lot of material testing and modeling, which you kind of see up here. We have a few material scientists on staff, so they'll help us understand, the material properties, structure, and chemical relationships between those things. We also do a lot of product testing. So instead of just testing a material itself, we might take your widget or your who's it or your what's it and run some tests to help you understand how it's going to perform once you get all these complicated things together. That also involves doing some failure analysis. And then we have kind of our suite of non-solid mechanics simulations over here, where we do everything from kind of just CFD. So whether that's some, pure fluids with some turbulence or laminar flow, but we also do electrochemistry, electromagnetics, multiphysics, heat transfer, and all of those things together. A little bit about our upcoming classes. So we have a couple webinars scheduled going into March of next year. So we have one here on practical polymer, material structure and characterization in the middle of January. You see a link to the free webinars down there on the bottom and training classes of the other one. We have one that shows a bunch of client stories in combination products in med tech and how we use multiphysics simulation and testing to help our clients solve those problems. We have one from another partner here who's going to be talking about adhesives and interfacial stresses and kind of how we help clients solve those problems. Then we have two of my polymer classes. So this one here, testing modeling for polymers for finite element simulation. That's an online course delivered in a very similar way. It's 8 hours total with a couple hours of what I call office hours, where you can come and ask me anything. And then the last one is a 2-day in-person class that we give here in the middle of May, where we do a whole lot of material testing, theory, modeling, and we discuss how you can put that all together via basically a 16-hour version of what you're going to get in about 45 minutes today. Taking a step back, I want to talk about kind of what we mean by material modeling, material model calibration, and validation. So this is the workflow that we use and we think about. You start over here on the left where you've got that, excuse me, got that testing where we're taking the actual material, we're performing some sort of mechanical test, whether it's tension up here, compression down here. And from that, we get our data. In this plot here, the solid colored lines are the test data that we've tested at multiple rates. And then we fit that model, we fit that data to a model, and that's fit with these dashed black lines. And you can see that we did these at 3 different strain rates and covering, you know, 7 orders of magnitude there. So we've covered that. From there, we get our material model or the material card, right? So that's a text file that gets output, and we often work in the codes that you see listed here. And then on the right, we like to do validation. So validation is a test that you've done that typically has a more complex geometry that you can do that test and then simulate the actual experiment with a finite element program, which is what you see over here. And then compare the, you know, for example, the force and displacement to look at what you're going to get out of that. And so that's what you see here in this example. And we have a very good fit between that finite element analysis and that experiment. You know, a little too stiff here, maybe a little soft there, but we're capturing the self-contact that you see there that drives that stiffness. So this is the workflow that we're going to talk about, and I'll tell you about some tips and tricks and methods that you can use to do all this. But taking a step back, we want to think about why we need to do this. I have an image over on the right of you know, a finite element model. This is a, you know, kind of fun one with somebody's glasses and an impact on that. But our inputs to any finite element model are really, we have 3 things that we need to do. We have the geometry, which is typically fairly easy. We know what the geometry is, or we have a proposed geometry. It might be difficult to do some meshing, but we can usually work through that. You have boundary conditions. That requires a little bit of engineering abstraction to potentially go from what is actually happening to something that we can do in a finite element model. And then we have what I think is the most interesting, which is the material behavior, a constitutive model. And for that, we need test data. That is most difficult. I find it the most interesting. That's why I spend my efforts at work kind of working on that. And it's interesting because for polymers in particular, there's time and temperature dependence that we really need to take into account. More than you'd see in metals at kind of normal rates and normal temperatures, you're going to get a very different response there. And you can capture that time and temperature dependent response with code native material models. And they get everything from viscoelasticity and creep and relaxation to anisotropy, failure, viscoplasticity. Any effect that we want, we can capture there. It's a question of getting the test data and using the appropriate models. So I'm going to talk about today how we can get all this in your model and some tips and tricks that I've done when I'm talking about testing or material modeling, and a little bit about that workflow. So again, I like to put this together. I like to put this up just to make sure we're on the same page, and hopefully you can use this potentially with your manager or your teammates to show them that you need this, right? Because we'll often have clients come to us and say, Sean, why do you need to do this testing? I have a spec sheet from my material supplier. Why don't you just use that? So this is an example I put together on a thermoplastic elastomer, or a TPE. That spec sheet had a couple things on it. It had a Shore A hardness, and then it gave us some stresses at 100% and 200% engineering strain. So if we look at these 3 dots, that's what I'm claiming I get from the specification sheet. Part of that is converting that Shore hardness into a modulus, and there's some uncertainty there, but I've done that in this case. So I can get those 3 purple points, and that's what I get from the manufacturer supplier. If I just take that Shore A hardness, I can come up with a neo-Hookean material model to match that slope. And that's already different from my purple by, you know, maybe 20% or so between, say, this point at 100% engineering strain. So, you know, I'm off a little bit there already from what they gave me, but I have a test lab. So I went back into my test lab and I took this material and I cut out a sample and I did a tension test. And that's what I get from this solid red line. You know, here you can see that these things match really, really well up to, however we want to look at these low strains, it matches well. The Shore A hardness matches well. The red matches this black curve. You know, that could be good. But over here at, say, 100% strain, I'm getting about 100% difference in spread here. So what's the right thing? Obviously, I think the right thing is the test that I did. I'm sure the supplier is going to say the test that they did is valid, and I'm not disputing that. But that could have been done years ago. Their method could have been different. We don't really know a lot of the details. So all this is to say that you want to be careful and you want to think beyond the spec sheet, particularly if you're using this material in a very critical application where failure is not an option. So hopefully that's giving you enough ammunition to go to your team or your manager and say, you know what, we really need to test our material if we want to model this accurately. This is a critical widget in our product, and we want to make sure it's going to behave, and we don't want to have to come back, cut a new tool, or do some redesigns or change the product specifications at a later date. So let's test this material, let's model it accurately, and let's go from there. So we're going to talk through material testing first, and then we'll get to model calibration and model validation later. So the first problem that we'll often run into with our clients is that for whatever reason, we can't get a standard test sample out of there. I've got two examples that we've experienced here in the past. So the first one is what's shown here. This is actually what's called a stent. So this can be implanted in an artery or a vein and help give it structural support. And this one in particular is made out of PLLA, polylactic acid. So that's a thermoplastic material. And the way that this is made is that the manufacturer actually extrudes a whole sheet, extrudes a tube of the thickness that they want and the diameter that they want. They get that out, and then they use a laser cutter to cut all these holes and give us this open structure. And that open structure allows it to embed itself in the surrounding materials, as well as makes it a little bit easier for the surgeons to install it. But that processing can definitely impact the way that our materials behave, right? You have an extrusion process, so you might be getting some alignment of the molecular chains along that extrusion process. We then laser cut this, so we're using heat, and these are pretty small areas and pretty thin here. So as we heat this up, we're going to get kind of global heating, and that could change the crystallinity of the material, and therefore change the material properties. And we have a very small thing. So what are we going to do if this is our material? The other example is, these are probably familiar to you. These are toy bricks that are used that kids like to play with. So the question here might be, okay, I know this material is an ABS material, and ABS is pretty good, but these are pretty small parts. These have pretty thin walls. I want to make sure that the injection molding process hasn't changed the material properties. So how can I do that? Because I have such small samples. So here we're able to extract those samples. We took a saw, we cut off a slice of it, we took that sidewall, and then we're able to get the specimen here, which you can see. But that's a very small specimen, which you'll see on the next slide. So, the first question is, I don't have much material, or maybe the material I'm interested in, maybe you've got a very complex injection molded part, but you only care about the material response in a very particular area where it's very thin, or you've got a lot of shear from your mold flow analysis. So how can I test that material right there? So this is something that we've come up with because we run into this problem a lot. We've developed our own dog bone sizes. So this right here is an ASTM D638 type 5 dog bone. If you're familiar with those, you'll see that that's kind of the standard size. We got 9.5 millimeters or so of gauge section, 3-ish, a little bit more than 3 millimeter width here. And that's that normal size. But we need, 60 to 70 millimeters in length here and 10 millimeters wide to get the sample. Those examples that I showed you were much smaller than that. So we've taken those dog bones and we've shrunk them twice. So we've done one where we keep the same width, but we keep the same gauge width, but then we kind of scaled everything else by about 50%. So you can see the length is half as long here. And then we have one here where we've then taken that one, scaled it down even further, and the gauge length is now 2.3 millimeters. So we've gone from 64 millimeters down to 16 millimeters total length. And this isn't the smallest that we've done. These are the ones we use most often. We had a client years ago who we tested a dog bone for that had a 700 micron gauge length and 700 micron gauge width. So we'll test down to that. And we routinely test things like fine wires and stuff like that that are very, very small. This is something that we're confident on because the idea behind these dog bones is very standard. We're using the same design rules, and we've done some simulation to verify that we're getting the stress state we want. but this is an option using custom sample sizes to do that. Have someone that I knew from grad school who I met up with a few years ago, and we were talking about our jobs, and he and I do similar things, and you know, he gave me the nugget that was we're experts in what we do. It's not that we disregard the standards, it's we understand why the standards exist, why they're there, and when we can change the assumptions and when we can modify those standards but still get the right answer. And that's what makes us experts in our field. And I really like that. So I'm stealing that and using it here. But that's really how we envision our material testing here at Verist. It's testing beyond those standards to help us understand the material behavior. And we can do that because we understand why the standards are developed the way they are. Another thing that we often like to do is some non-standard loading. This is one example that we do very often. This was at a fairly high rate, but we like to do or a fairly moderate rate. We like to do cyclic loading. So in this case, an ASTM test on this thermoplastic material would typically say you just pull this until you get to failure, and then that's it. But I think you're leaving a lot on the table and not getting all the material information that you need. So why would we do something else? Why do standards ignore this? Standards ignore it because they can make the data a little more difficult to use. It makes the test a little more involved. Some of your assumptions might start to break down. But if we're measuring our stress and our strain accurately, we can give it any load history we want. And this is why. I mean, these are three things that I think that we really get out. Three additional things that we really get out of here. So if we look at that same test in that stress versus strain space, this is a thermoplastic material. It shows necking, and I can tell that from this drop down. I believe this is a polycarbonate. So we get a couple kind of effects. The first one is this purple line here, right? We're seeing a stress relaxation. So in this one test, I get information about the modulus, the yield stress, kind of the shape of the curve. But then I say, okay, at 20% strain and 30 or 60 seconds, I'm getting, about 20% stress relaxation. So that can be very valuable to me. Even if I don't explicitly model that, I might be able to say, okay, I've got this part loaded. I know that the stress is going to reduce 20% after it's gotten past its yield point. I get a lot of information about kind of how much of this response is plastic behavior and permanent deformation, and how much of it might be recoverable. We also get information about the unloading slope. The unloading slope for polymers like this doesn't always match the unloading slope the loading slope that you have here. So being able to capture that can be helpful if you have multiple loadings of your material. And then we get this interesting effect, which is something called rejuvenation. So that might tell you what some interesting things that might happen to your material when you load it multiple times. But even taking a step back, I've just called out three things here, but this has a wealth of information, right? We ran this test. We've done all this work. It's a shame to just say, okay, we actually only have four numbers. We've got a modulus, we've got a yield stress, we've got an ultimate strain to failure or failure strain, and we've got an ultimate tensile strength, right? But if we do that, we are going to lose a lot of information. So having all of this data here is critical and something that you really want to make sure that you're doing. With that, we really want to make sure that we're getting some advanced methods when we're in our testing itself. So I'm showing you two examples of digital image correlation, which I'll talk about in a little bit. But this is a video that we take, and you can see that we're measuring the strain contours there. That is the axial engineering strain. So instead of using an extensometer or the crosshead displacement, we can measure that. Here we see a couple interesting things, right? You see those holds, that pauses in the video where the strain is constant. That's where we're doing those holds. But we see that we're getting a very nice uniform strain field throughout here. A little bit of necking there, but then the sample breaks. But we can also do things like measure the shear strain during a test like this. So it gives you a lot more information. It also just gives you a video record of the test, which is always helpful. You can come back the next day, a week, a month later, and see if you see an effect there. But there's additional data that we can get out of that. So we're going to be talking about that on this next slide. So this is an example I put together years ago at a conference to talk about digital image correlation, how you can extract more information. And this is that necking phenomenon of polycarbonate that I was talking about, where you see that the strain localized and you're getting a higher strain value here than you are here. Our test methods kind of just normally just take the average between here, but we've got this gradient, we've got a thinning here. So can we use this information to our advantage? And what would the valid strain measurement be? So I look at this and I can easily define 3 measurements. I could do what we would have done, years ago with an extensometer, where I clip something here and I clip something here, and I basically measure the displacement between those, and I know the displacement between those, and I basically get an average strain. The other 2 things that are fairly obvious is I could take an average here and looked at what's happening in the region that's not necked, and I could take an average here that's looking in the necked region, and which one of those is valid, which gives what information is useful, and what can we do with that. So again, here's that test data showing the stress versus strain. It's that same one that we looked at previously. We've got this peak, this drop, all that kind of thing. Your first question might be, Sean, what stress history or strain history is that? Because you've just showed me 3 different strain histories. The answer is that was that one in the middle. That was what I call the virtual extensometer. But to not spend too much time going through this, we can also look at what happens if we have, if we look at those 3 different histories. So this is just looking at the strain versus time for that test that I did on that dog bone. And you can see that I've got 3 different curves there that are solid lines, the green, the red, and the blue. So the green is what's happening in the necked region, the blue is what's happening in the unnecked region, and the red is what's happening as the virtual extensometer. Right, and you can see I've got 3 different strain histories. They start together, and then somewhere here at about 300 seconds, you see that the unnecked region just goes completely flat. I'm not getting any strain grab there. We do it unloading, no strain, and then it starts to increase and it comes up here. Conversely, the green one, so that necked region where they split off, the strain rate shoots up and you get a lot more strain. Then you continue to get some, but it kind of plateaus, it slows down. And then, as you would expect, the virtual extensometer, which is the average, just kind of goes in the middle, and it goes along. They all come back together here. There's a little bit where kind of one goes over the other. So that's probably a little bit of experimental error, the variation between them, but then they kind of collapse up here at about 100% strain. So the dashed lines here are predictions from what I call an inverse calibration, which we'll talk a little bit about, but you could also call it validation. I took that dog bone, I meshed it, and then I simulated the displacement history on there, and I saw the necking in that material. So then I grabbed those exact same 3 different strain histories. So in that one sample, I've extracted 3 strain histories that I can reasonably say are something that a lot of the material experiences, and I can predict that with my material model as well. So I can get that necking where I get some localization. Now you might say to me, Sean, this is not perfect, this is not great. I agree, maybe I could get a little bit better. Maybe I was hitting the limits of that particular code or that particular material model, but you can capture that necking effect and those different strain rates. And so this can be used to help us improve the accuracy of our model. If we only use the average, we could get that necking effect, but we've done the test, we have the data. Can we get more information out of it? And can we make that useful and make our material models more accurate? So still on to testing, I want to talk a little bit about rate dependence because it's very important in polymers. So the first one is, what do I mean by rate dependence? So this is some test data that we've done on our in our lab here on a material. I think this is an ABS. So you can see that we've tested this kind of at 3 different rates. At the darkest blue is 1 times 10 to the minus third, the light blue is 0.1, and then the red is high rate uniaxial tension at 500 strain per second. Right, so there are 2 interesting things we see. First, the modulus doesn't change significantly, but second, the yield stress does change. So down at the slowest rate, it's, we'll say 59 MPa, but it's up here at 82, 85 MPa. Right, so if you're designing something in an impact application, but you're using this value, you're going to be over designing your part. You're going to be spending more time, more money, more material resources, all those kinds of things that we don't want to do. Kind of the next thing that you see is that the kind of the plateau stress gets higher with that yield stress. What I would say is we've got, and then we can look a little bit at failure. I would basically say this material doesn't have rate dependence on the failure. You see that it decreased and then it increased. So you might say, Sean, there could be some experimental errors there. It definitely could be, but what I would say is we've got 2 data points on each one of these. We'd need more to make an actual determination of that. So we see these different types of behavior. We see that the material stiffens and gets stronger as we pull it faster and faster. So how can we test that? What can we do? So this is a slide kind of showing a wide range of tests that you can do on your material to understand the behavior. So I have here, we're going to talk through these 4 just kind of briefly. And the first one is what most people are familiar with. You might call this an Instron. We use a different company, but the idea is the same. I'd call this a typical or a standard load frame. This is electromechanical. There's servo hydraulic. This black bar moves up and down so we can push or pull things. Got a chamber here. You know, if you were like me in your undergrad, you might have done a, aluminum or steel testing, lab where you took a dog bone and you put an extensometer and you pulled it and you wrote a report about it. It would have been done on a machine similar to what you see here over on the left. Kind of the next step is what we call an electrodynamic or a fast servo hydraulic machine. Again, this is ours, which you can see here. This one we can also do fatigue on, but the idea is basically the same, but it can go much faster. So this one can go up to about 200 millimeters a second. We can run it at a couple hertz, which is useful for us for fatigue. It can go up to 20 or 40 hertz, but generally for polymers, if we're at that level, we're going to start to see some sample heating, which we want to avoid. But so going at those rates by some nice sample design, we can generally get up to 10 or 20 or 30 strain per second. So we'd kind of get up to this range. Now, if we want to go to the next level, we use a drop tower, which you can see the Varus Engineering drop tower here, kind of highlighted with that pinkish color. So that'll get us somewhere up to about 1,000 strain per second, 2,000 strain per second. Again, if we can design our sample well and we have the right amount of material. And then kind of beyond that is what's called a Kolsky bar or split Hopkinson pressure bar. This is a picture of the bar that we used to have here at Varus Engineering, which we don't have anymore. And we kind of moved away from that for a variety of reasons. There's nothing wrong with it, but we just found that we were using the drop tower more and more, and we wanted to capture that space to use for other equipment. I always like to put at least one high-speed video. So you can see a high-speed video of a split Hopkinson pressure bar test, and the first test happens right there. So the entire duration of this video is about 200 milliseconds. That part of the test is about 10 milliseconds long, where you get that loading. Talking a little bit about our drop tower, I just kind of wanted to show an example on kind of why we developed it and why we think it's better. Because there are other drop towers or other high-speed test systems on the market. So we took one of our materials, which I believe was a nylon material, and we tested it about 750 strain per second on our drop tower, and that's what you see in the green. And then we had the material tested by a competitor's product. So it was on a servo hydraulic machine. And we got back from them the red. So, there are a couple issues here, but the biggest one is kind of the noise and the data quality. So this red material, shows what I would say is unphysical, right? We see these kind of 4 or 5 vibrations and peaks here that are not in our data. And there are 2 things that you might see. First, those vibrations are unphysical. And you might say, Sean, I might ignore those. I know those are unphysical, or I might get rid of them. That's okay. But if you didn't have this green data, it would be hard for you to say, is the yield stress 100 MPa, or is it 90 MPa, or is it 80 MPa, or is it something down here, right? Because you've got that dynamic noise that's happening there, you don't know what's going on. You also have that, their test showed failure at about 100% strain. Ours, we had one here at 125, but 2 here up at 250. That's, I don't think, a limitation of the machine. I think we might have been a little more careful in the setup. But, we like to show this to kind of, we like to say that we really care about the quality of our data, and we work as hard as we can to get that. And the drop tower is a reflection of that. This is a concrete example where you can show the comparison between what you might be able to get with somebody else's system, what you can get with our system. Similarly, we do like to take another high-speed video. So this is one on a very brittle material where it failed at about 2% engineering strain. but you can see kind of the quality of the test there and the data that you can get out with the strain. So just a nice fun video at about 100,000 frames per second. This is a polymer material, but it is something that that is much more brittle because it was a very highly filled polymer. We're going to move on now to material model calibration, which you can kind of see there in the center. So you've collected your data, you've done some non-standard tests because you've gained the confidence from this webinar. You have the data, but what do you do? How can you use that data in your model? The answer is that there are a lot of kind of programs out there to help you do this. Most or all of the finite element companies now have a program that allow you to do some material calibration or material model optimization. And then there are third-party tools as well. But the advantage here is that with these, and if you use this workflow here, you can utilize those complex load histories that I had. The idea is very similar. Is very simple, excuse me. We're gonna do a single element, finite element simulation, and it's going to be a unit cube, and we're going to apply our displacements that we did in the test. So if we loaded it up and held and unload and all that kind of things, we measure that, we know what it is, so we can do that. So we do that single element, we apply that, and then we're going to extract our stress and extract that stress from the applied strain and compare it to our experiments. And then after that, we're going to modify our material model, and usually we want to do that in a nonlinear optimization way, where we give it the model, we give it the 10 parameters, and we say, use nonlinear optimization to find these best parameters. And you're just going to keep doing that over and over again until you get that. So that's a nice schematic, but how does that work in practice? I'm going to kind of show you what happens when you're looking at that material response as you're doing the calibration. So I took some test data again on that ABS that we were looking at previously. I chose a model. The exact model here is kind of not really important, but basically I said, all right, I'm going to choose the parameters, and I'm going to choose them to be as good as I can, kind of manually doing this in 15, 20 minutes, right? And this is kind of what I was able to get to in 15 or 20 minutes of work. I'm getting some of the broad features. The stiffness is kind of right. I'm getting the unloading moderately well. My yield stress here is low. My yield stress here is way too high. I'm not quite, capturing this kind of necking and drop here, but I'm getting it somewhat, So, I'm okay, but I think I can do better than this. But I don't want to spend hours or days of my life kind of choosing numbers and going from there. So I'm going to do that, and I'm going to start to run that optimization with the program, and update the material model. So as we go through that, we're going to see that the model starts to get a little bit better, kind of quickly get something, significantly better. If we go back, we were here, now we're here. The error is getting better, the shape's getting a little bit closer, our yield stresses aren't as far off. So we're making progress. We're getting that cyclic loading pretty well. And then it gets a little bit better as we get closer and closer to the final. And then here we get kind of the current results. You actually saw one of the yield stresses go up, but what we kind of saw is that we're now capturing that shape a little bit better, and we're kind of matching this in an average sense pretty well. So we go back through that, we started here, and then quickly kind of made it to here. And part of that could be the kind of the cyclic loading where we see that the peak is a little high. I wouldn't say that I'm, done with this material model, but this shows you what you can do. So this was after I got the test data, I was able to get to this point where I did 20 minutes of manual optimization, and then I just let my computer run for like an hour or so, and I was able to get here. So that's, that's what I'm talking about. That's what we can do. That's how we can optimize this to get a material model for us to do finite element analysis. The last part in material model calibration is what we call inverse calibration. This is sometimes used in validation, which I'm going to talk about next, or sometimes if you've got a non-standard part. So this is kind of doing a ball impact test on a specimen that you see here. I have a non-uniform stress state. I can't write down what the stress is, but I can measure force and displacement. So how can I use this? The workflow is the same that we looked at for the material model calibration. You just have a longer simulation. So you have a full finite element mode. You're going to finite element model that you write an input file to. You're going to run it. You're going to extract that force versus displacement and then compare it to your test data and then optimize it from there. So again, this is a workflow that we do a lot, and whether it's something like this ball impact, a dog bone like you saw with that DIC example, or something more complex like that compression of that 3D printed lattice structure, doing an inverse method is definitely something that we can use to help understand material properties in a more complex stress state. The last section that we're going to talk about here is what we call model validation, when it's you working with your internal teams, it's maybe convincing your peers and your management or the group that you're working with that your model is accurate. Here at Verist, it really helps our clients build confidence in the work we've doing. They've handed something off to us, and if we can show a validated material model by doing these tests and simulation, it can go a long way to help our clients understand the accuracy of our models. So these are a couple examples of validation tests that I like to do. So on the right, you can see that ball indentation test, which I talked about with the inverse calibration. It's pretty simple. You take a very hard ball, you take a softer material, you push them together, and then you get a force versus displacement. This one, sometimes I'll use this for shear testing, but I also like to do something, you can also do this for validation because it is shear, but it's shear dominated. It's not a perfect shear state. Or you can do like a hole in a plate test, right? So we get some stress concentration, you get some higher areas of shear. So it can be very interesting to do that test to do that. So these are some of my favorites. But one thing I want to talk about here is friction, because friction can be the bane of our experimentalists' existence. So we did a case study here where we took this ball indentation test, which is a nice complex stress state. We ran on a universal test frame, and I measured the force versus displacement. I calibrated a material model to it, and I wanted to see what happens as we change some conditions. One thing I like about this is you can use larger balls, thinner balls that get different stress states, all those kinds of things. So relatively small changes, you can change the response of your material. So we set up a finite element model. In this case, we're doing an axisymmetric one. Some information here over on the left. We're doing something with a hyperelastic model for it, just for ease of convergence. We've got this nice mesh, and we're going to kind of compress this and see what happens in this area and see what we get out of the test. So I did that, and I changed the coefficient of friction from mu of 0 all the way up to mu of 0.5. And you can see here for the first, little bit of applied displacement, which I'm calling engineering strain, but that should actually be displacement. I apologize. So as we get up to 0.4 millimeters of displacement, we basically have like no difference between these things. But as we go to higher and higher forces and displacement, we start to see some divergence. So if frictionless, we're at 55, 56, but here we're up at 71. At first you might think that's not that large, but that's a 30% increase in the force that we predict at those highest displacements. So, if that's relevant for our, that a 30% error could be, very relevant to our design, particularly if you start to stack up compounding errors between a material change or some stiffness change or some loading change. You could very well get into an area where you're not going to perform as you want. I like to show this just because it's very critical to think about the friction and think about how that's going to change your material response and how you simulate your test, because it could introduce a lot of error. You don't want to tweak your material model to account for friction errors, so you want to make sure that you understand the friction state. To me, that usually means I want to reduce it as much as I can, because the difference between 0 and 0.1 here is more on the order of 4% or so. And that's within kind of measurement error that I'm going to get anyway. If I ran this test 100 times, I'm going to see a spread like that anyway. So trying to chase that error down in my material model or the finite element model doesn't make sense to me, because I'm going to see that much material variability from the same lot of material. And then if I'm making these widgets for the next 10 years, I'm going to see a very different response as I make those different ones. That is what I have together for you. So thank you for taking the time today to meet with me and discuss material testing, material modeling, and validation. Right? As CAE engineers, we can sometimes be have our blinders on and just use a specification sheet. hopefully if I showed you that, well, that's why that could be an issue. And really what we want to do is we want to come back to this workflow. We want to be doing this on our materials to understand how they're going to behave so that we can then accurately model that and get our partners, our teammates, the best design we can and give them the most accurate predictions that we can. So I am going to pause there, but open it up for any sort of questions. So if anyone has a question, I would love to answer. You should be able to kind of put something in the chat. Let's see. So I have a question here. Does the sample size yield in different material properties? That's a great question. So if your material is manufactured the same way, a larger versus a smaller sample should not give you a different material behavior. You should be able to have a very large dog bone versus very small dog bone to get the same thing. So sample size doesn't inherently affect those properties. The part that it could be an issue is when you talk about how that was made. So, you know, if you injection mold something very, very thin, you can get a lot of built-in shear stresses and a lot of polymer chain alignment, and that could change your yield stress or your stiffness. Or if you have, you know, a different manufacturing process, that can too. One of a really great example is, you know, the old plastic grocery bags that you'd get are made out of a material called HDPE. I'm going to simplify it, and HDPE that you get there is usually multi-layered as well, which makes it a little more complex. But they make those very thin sheets by taking a big piece of HDPE and extruding it. And that extrusion is applying force and making it thinner and, you know, pulling it in the tensile direction. So that means that you've aligned those polymer chains and you get a much stronger response. So if you take that same grade of HDPE and injection mold something versus the bag is going to show a much higher yield stress than just the injection molded HDPE because it hasn't gone through that mechanical working. So that's why you want to be careful and understand. That said, most parts injection molding, you know, you can usually look at it and with a good eye, you can understand if it's going to be a problem. You can do some further analysis as well. But I don't worry about just a large versus a small sample. I worry about how they're made and whether that's going to change the process. Someone asked, can we get a copy of the slides for reference? Yeah, so probably early next week, you'll get an email with the slides. With the slides. Well, you get an email with an access to the video as well. I'd be happy to share the slides with you if you send me an email, and I can send those out. But you'll get an email either tomorrow or on Monday with the link to this video. And if you reach out, I'd be happy to share some of this content with you. So do you recommend to lubricate the test to rule out friction as much as you can? So generally, yes. And I do this both for compression tests as well as kind of that indentation test that I was showing. Mostly because I would like to reduce friction as much as possible because that makes my life easier. Other people will take like the other where you want no slip. That can work well for that indentation test because it's very easy to model. But if you're doing a compression test, I don't like that because it gives you a non-uniform stress state. And we've done some simulations to basically show for what we think are reasonable values of friction, 0.05 to 0.1, you know, we get like a 1 or 2% error for most materials at like 50% strain. So that's a pretty small error that I'm willing to live with. What plastics should you complete cyclic loading versus just simple uniaxial tension testing? To me, it's less about plastics because basically all of them are going to show those kind of relaxation and unloading and reloading effects. The question is really, does the unloading or multiple loadings matter for your application? So, you know, if you're never unloading it, then you don't care. But, you know, we'll talk to people and we're doing some impact simulation and testing. And I recommend these cyclic tests and like, well, I don't care about cyclic tests. I just hit this thing and then that's what I get out. But that cyclic test gives you the information about how something's going to rebound off of it. Or if you drop your phone, that kind of plastic deformation, that loading and unloading you get will tell you how much of that energy from the phone case kind of makes it bounce back up. So it's very important. So So I would say all polymers should be cyclically loaded if you're going to model them, but really it's a little bit more about what what's your loading scenario. If you don't have a loading scenario where unloading matters at all, then you might not need to. Let's see, another question here. Let me take a quick drink. How do we decide loading, unloading strain for cyclic loading test and calibration process? Slide number 19. Is it a problem if the curves intersect in the graph for calibration purposes? I'm not sure I understand that second one, so if you could add a little bit more there. But how do we decide? That's a combination of what I think is interesting in the material and what's interesting in the loading scenario. So if I know like that I'm going to be I expect my loads to put about 5% strain on it, I'm going to want one or two of my cyclic loading points around 5% strain, 4%, 7%, something like that. So that's one thing. The other thing I like to do is I usually like to take a couple points before you see yield. So if I come here and I go to slide 19, right, so yield would be about here. I'd want maybe 1 or 2 points before yield to understand how much plasticity we see before yield, because you will see some plasticity. And then I might do 1 or 2 afterwards. Again, using my application as a guideline for choosing some of those strains. Let's see. Also, in your DIC results, does averaging the entire field of view is a meaningful way to use DIC? What percent of standard deviation for polymers does Varus consider good for test data? Oh, that's a very difficult question. The second one, what's kind of the standard deviation and where does that matter? So you're talking about here. I would say, so averaging the entire field of view, how I have these contours drawn currently, I would not do that because I intentionally kept some things kind of out of the gauge region, right? So my stress here, my stress right here is less than my stress here because I've got more material. If all I had done, if I had, for example, kind of cut this off here, and I'd only had the area between there, then you could take the average and I think it would make physical sense. But the way I've had it drawn, it wouldn't. If it was just between this area, I would expect the average of all those points to be the same thing as a virtual extensometer. So is it a problem with the curves intersect in the graph for calibration purposes? I think you might be talking about how this dark blue one goes over this one here. The model won't capture that unless you turn on some things. So there could be a couple things happening here. It could be a testing error. That's always potential. I don't want to pretend that it's not there. There could be some sample heating. It could be failure processes starting differently. So your model will not predict this difference unless you kind of add some other special features that, in my opinion, are getting other physics in there. So it's a little bit of a problem, but you can still calibrate to it. So Ryan, someone is saying, Ryan's saying to Kartik, the flaw size or flaw density may play into sample size effect. That's a good point. When you get to failure, your defect density matters because that's going to be where you initiate. That said, I would expect the average for a small sample to match a large sample if you can, get statistics on 20 or 50 samples of each. But you might see a different distribution or different occurrence because of that. Sean, thank you for the condensed educational well-structured webinar. Oh, thank you. What failure model would you recommend for hard thermoplastics such as polycarbonate ABS for part-level multi-axial loading? One of the most important questions in structural design is it going to fail? Well, Kenwan, that is a very interesting question. And part of the answer depends on kind of what you're working in because each code is a little bit differently. I'll say first that I won't model failure unless I'm doing an explicit simulation. It's very difficult to do with an implicit simulation. And you spend more time kind of trying to get the solver to do what you want than actually doing analysis. So for explicit solvers, I work in Abacus, Elastina, and Radios. They have basically essentially similar material models, but essentially what you need to do is you need to give them kind of failure strain versus strain rate, because you can see strain rate dependent failure. Here we don't see a huge effect in this particular material, but then the other one is triaxiality. So triaxiality is a scalar to look at the stress rate. It is the pressure over the von Mises stress, or maybe the negative of the pressure over the von Mises stress, depending on how you define pressure. And it's a scalar that goes from negative infinity to infinity. But if it's 0, you're in pure shear. If it's 1/3, you're in tension. If it's negative 1/3, you're in uniaxial compression. 2/3 is biaxial tension. So usually I start there, and I will perform tests at multiple triaxialities and then look at that. That is kind of the next level and what I do. As for exact models, you know, essentially, I have found that you want to do some sort of table lookup models. There are like models that are based on phenomenological work for metals, like the Gerson failure model, and Needleman. Needleman has one as well with a name I don't remember how to pronounce. And then there are a lot out of a group at MIT who do metal for automotive applications. So they'll look at aluminum and steels. And I'm blanking on the name right now. It's where's Bicky? Bicky has 3 or 4 that has come out of his group there. So those even get more complex using another invariant of the stress to define that and require even more tests. So it's hard to say what a go-to model is other than collecting the data, doing inverse calibrations, and setting those parameters based on those. But, if you ask me just what's the best, stress strain response for a polycarbonate, I have my answer for each finite element code. But for the failure model, there's basically one, and it's a table lookup. So hopefully that was helpful. But you need a lot more data, you need a lot more input, and you need a lot more setup to do that. So that was a lot. You know what? It's been on my list to put together a webinar on failure modeling and polymers. So that's just gone to the top of my list for kind of early to mid next year. So I will do that. But hopefully that was helpful, Ken. Let's see. What type of experimental data are needed in order to find the best material model calibration? Is that an alpha super uniaxial tensile test or compression or shear test? Is it not mandatory biaxial test? That is a great question, and I could talk for hours about that. The answer is it depends on your material, and depends on your loading. For most elastomers, I will just do one uniaxial mode. I find that the difference between shear versus tension versus biaxial tension is very small, and sometimes less than the experimental error by doing those harder tests. So I find that it's not necessarily worth it to do that, and I use a model that doesn't then need that input. That said, if we start to talk about thermoplastics, you have different yield and tension versus compression. So you want to do some multiple tests. You could do tension and compression, tension and shear and biaxial, whatever you kind of are set up. Generally, 2 to 3 modes gives me plenty to understand that pressure-dependent response, and I'm happy with that. It does get more complicated if you start talking about fiber-filled materials, because you've got anisotropy. Then you're going to want to start to talk in different directions. We are going to have a webinar on kind of anisotropic materials in the coming months. We're kind of putting that content together. We have a new expert, Chris Noble, who's done a lot of work in that area. So he's going to be putting together a webinar for that. So keep an eye out. All right, will the recording be made available to share for people that did not register or attend? Also, can you do multi-axial loading tests by axial tension, triaxial compression? The people who registered will get an email with a link, and they will see that. We also generally put this on our YouTube page, put our webinars on our YouTube page. So if you go to, I don't even know the URL, so that can't really help you. But if you search for Varus Engineering on YouTube, it should be up there kind of sometime next week. And Ryan, if you send your email address, I'll make sure I can send you that link. Happy holidays to you too, Ken. Thanks, Jinling. Josh says, how many tests on average does it take to characterize a polymer elastomer for rate and temperature dependence for an impact application? I generally like to do 3 repeats at like a particular rate. And I see that someone has their hand up. I'll call on them in a second. So I generally, if I'm just looking at stress strain, 3 repeats of a particular test condition are plenty. Generally, if it's a well-behaved material. The caveats to that are if we want to get failure data and you want some statistical data, we need more, and part of that's going to depend on what type of material. Is it ductile failure? Is it brittle? So that partially answers that. The other thing that we might want to talk about is the temperature that you're at. So if you're near the glass transition temperature and you're doing some testing, I generally ask for more, because temperature and rate dependence are highly correlated and intertangled in polymers, and you'll see more variability. So we'd want to nail that down a little bit more. So at an impact application, again, if we're just talking about stress versus strain, I'll do 3. Clients will ask for 5 sometimes. I'll do it. I don't think there's a lot more value there, but happy to do it. I don't like to do less than 3, because when we do 2 and you've got a difference between 2 tests, what was the issue? Which one's right? You don't know. You have to run a 3rd test to understand if one was right or one was wrong. So that's kind of there. ASTM standards typically say 5. We say 3 are plenty. Thank you. So I know someone had their hand up. I don't know if they had any more, if they had a chance to ask their question, but I will stick around for another minute or two. Again, thank you for attending today. You should get that email. Please feel free to email me if you have any questions. I'll gladly send out some more information and some PDFs as well if you get in contact with me. Otherwise, thank you very much. Have a happy holidays, and I'll stick around for a minute. So. All right. Looks like everyone's dropping off. Thank you very much. Hopefully I'll talk to you all soon.